Okay, so I'm going to recap that for future audience. This Olelo describes my experience with the lab, and I'm super grateful to Pat for just giving me the freedom and dignity as a scientist to make my own independent decisions. And also, I did spend a lot of time in the lab selecting songs, and I'm a singer, so it's just felt like very articulate and wrapping things up and describing what I was doing. I know we usually end with mahalos, but if I completely lose my audience's attention, that's not these folks' fault, and they deserve a lot of recognition for all the support they've given me. So I've already thanked Pat. I'd also like to thank Thomas Ibanez, who's been the statistical brains behind a lot of what we've done in this. Thank you, Adam, for your support and your encouragement along the way. It's been wonderful having your expertise as a bioacoustician. Amanda also helped me a lot with statistics, like on the ground here, and it was so great having you and just having your friendship too throughout my journey in this lab ever since we met at that virtual HCC. There's been so many people who have helped me, and I'm grateful to Hakalau for giving us access to the field site as well as the Heart Ohana. Thank you to the DoD and WT Yoshimoto Foundation for funding my graduate school and tuition. Thank you to my annotators, Saxony, Jen, Mackenzie, and Keely. I couldn't have gotten through all those songs without you. And everyone, if you've helped me in the field, if you've been down that transect or one of the transects, I really greatly appreciate you. And then finally, Anne has helped me with so many technical snafus, vehicle snafus, Raven issues. I really appreciate you, Anne. And finally, although the National Park Service Pacific Island Inventory and Monitoring Network was not paying me for research related to my thesis, they did help to keep me employed so that I could sustain myself through the end of this. So thank you, PACN. And if you have contributed to my development as a scientist in any way, if you have supported me on my journey from the very early stages, and if you are listening to this right now, thank you from the bottom of my heart. Your fingerprints are on these projects just as much as mine, because you've really shaped me as a person and as a scientist. So mahalo to you. And finally, mahalo to the Manu. This work is dedicated to them. And I think that our Manu deserve every bit of acknowledgement we can give them. They play critical roles in the forest ecosystem as seed dispersers, as pollinators. They also have not just biological significance, but cultural significance. So across cultures, birds are associated with the divine, with freedom, with something spiritual. And in Hawaiian culture especially, they feature prominently in the Kumulipo, or the Hawaiian creation chant. And many are seen as Aumakua, or family gods. So our Manu are very significant, and honestly, they've been my greatest teachers these last 2 years and beyond that. So thank you very much. And now I'm gonna finally transition into the work that I've done. So this work focuses on the applications of passive acoustic monitoring. Don't worry, I'm gonna define what that is. And it's coming in 2 parts. The first question is a theoretical ecological question. And then the second question is, can we apply what we know from bioacoustics to improve population wildlife monitoring? So this isn't the last time you'll see these questions. I'll revisit them. Okay, so first of all, what is passive acoustic monitoring, or PAM? Passive acoustic monitoring uses automated recording devices, which are recorders that can set their own schedules. We put them out in the field and they observe the sonic environment, or the soundscape, and I'll be using that word a lot this morning. These are our ears in the forest, and they have some really great benefits. First of all, they can continuously record data while we take a nap, because we can't be surveying birds 24/7, although I would love to. They're minimally invasive, so they're not creating disturbance in the way that bird surveyors would. They're cost effective when you consider the fact that it's kind of nice to pay people like me to go do the surveys, but if you invest in the technology, it can keep surveying and you only have to pay for the device once. They can also improve human safety. Many of these endangered forest birds are in very remote places, and it can be dangerous to access them, even require flying in helicopters. They're also less reliant on people being seasoned in shape field experts who know the terrain and the lay of the land, but they're not perfect. So they lack that visual sensory component that we evolved apes have. They have smaller sampling radii, so I can usually hear further than a song meter can. They take a significant amount of time to process the data because they collect huge heaps of it. And then there's also technical interpretation of that data. Sometimes this even requires advanced knowledge of machine learning or identification of hundreds of different species. So we haven't completely gotten past the technical expertise obstacle. And then finally, I've experienced this personally, is they have malfunctions. They say that they're waterproof, they're not perfectly waterproof. And also you have to do maintenance on them regularly. So whether it's rain or shine, if my song meter's batteries are gonna die, I need to go down the transect and service them. Okay, my first question is, does the presence of introduced birds in a community influence the amount of acoustic overlap between species? So again, this is a theoretical ecological question. Welcome to the soundscape. Within a soundscape, native species use vocalizations to attract mates, to defend their territories, and to warn others of danger. They can even use it to deceive predators or competitors. And there's a theory called the acoustic niche hypothesis, which says that native species in a pristine environment have evolved signals that are different from other species in the frequency bandwidth, which is shown on the y-axis here, and the time sequence, which is shown on the x-axis. So you can see that these two vocalizations, the darker black vocalization and the gray vocalization, are overlapping in both frequency and time. The acoustic niche hypothesis says that animals have simply evolved to avoid that issue. So this is in a pristine natural environment, but what would happen if you introduce new species into an environment? Well, the literature on this is pretty limited, but we do know that bullfrogs in the Amazon have caused native frog species to shift their frequencies up and to drive their call rates down. And then similarly, red-billed lathrix, which are also introduced in Hawaiʻi, in Italy have caused Eurasian blackcaps to shift their songs in time. And I'm going to unpack that second study in a little bit more detail later. Why does this matter? Is it a big deal if animals have to change their vocalizations? Well, this is mostly a theoretical framework, but there is evidence that they have to consume more energy and they will mate less because the invasive species are interfering with their signals arriving to their target audience. However, all the literature so far has just focused on a single invasive species. But what would happen if there's multiple invasive species? If there's a selection pressure in one direction, it might be manageable for an animal to change its behavior in a different direction of that. But if there's selection pressures operating from multiple directions, where does a native species go with that? That's what I wanted to at least start to answer with my thesis. And Hawaii perhaps is no better place to study that question because more than 2/3 of our native bird species have gone extinct, largely due to avian malaria, introduced predators, habitat destruction, and degradation. And then subsequently, we've released over 160 species of non-native birds, and many of these have established and become dominant members of the soundscape or the acoustic environment. So Pat and some others in our lab did a previous study looking at, okay, is the acoustic niche hypothesis operating in Hawaii? And they found that there was a significant amount of frequency overlap, mostly among native species at Hakalau, but also with some introduced species, and that seemed to have been accounted for or mitigated by temporal overlap. So I'm going to unpack that second figure real quick because it could be a little confusing. Those box plots are showing the results of a null model, which is taking songs, taking tracks and slicing up the songs and reshuffling them through the track. Each song is kept the same length and the frequencies are kept the same, but they're randomized. And so what that null model gives you is a distribution of songs and how often you would expect those songs to overlap by random chance. The black dots are observations. The box plots are the distributions of those overlaps with means in the middle. And then dots with asterisks next to them are significantly different from the null distribution. So in short, what they found was that the number of overlapping vocalizations was less than what we would expect just due to random chance. So there is evidence of acoustic niche partitioning in Hawaii, according to this study. However, I don't think that this is the full story. So all due respect to Pat and the others, they didn't compare acoustic niche partitioning between native and non-native species. And understandably, because there's very low densities of non-native species at Hakalau. So that's what I wanted to unpack. Okay, back to the Laethrix. So in Italy, the Laethrix has become one of the most abundant sonically active or singing birds in the soundscape. And what blackcaps have had to do is learn how to sing in between the songs of red-billed Laethrix. So I figured that could be happening here. And my question is there an effect of introduced species presence in the community on acoustic niche partitioning and forest bird communities on windward Mauna Kea? I figured that as the representation of introduced species in a community increases, the acoustic overlap would also increase, simply because these introduced birds have a recent history here within the last century, and our native birds have been co-evolving for thousands to millions of years. So the recency makes them less likely to have separated their songs in frequency and time. To accomplish this study, I had two field sites. The first one was Hakalau, and my reason for choosing Hakalau of all places is that it's the closest to historical conditions in Hawaii that we can achieve. If I had a DeLorean, I would go back and try to get recordings of before all the extinctions happened. Well, first I would try to stop the extinctions, but I would also try to get recordings pre-extinctions and also get recordings pre-introductions. But unfortunately, we can't do that, and we didn't have the technology back then. The closest that we can do is record at places like Hakalau that, one, have very low densities of introduced bird species, and two, have the highest native bird diversity in the archipelago. So I chose a variety of vegetation sites or vegetation types because that's known to affect sound transmission. I won't get into too much detail with that. But Hakalau is interesting in that a lot of the forest is actually recent secondary forest that's starting to come back. It's a result of significant outplanting efforts that Pat was a part of. And so this new forest structure, I think, could have slightly different properties and has more introduced birds than the continuous primary wet forest that's mostly ohia and koa. My second field site was in a coffee orchard in Pauka'a at low elevation, which is almost entirely introduced bird species. And this is mostly alien grasses and non-native trees, but there is an abundance of birds. My recording ran through the summer months of 2022, and I tried to get a minimum of 30 days of recording for each site just to keep things consistent. We were limited on the number of song meters, so sometimes I had to run song meters on alternate schedules, but I tried to rotate them every 2 weeks so they were getting capturing the full variation within that season, and also had consistent sampling effort. The song meters were programmed to run from sunrise to 11 a.m. because that's peak bird activity. And then they were on, for the most part, a 5 minutes on, 5 minutes off schedule. I did have some other song meters that Pat was using for separate studies. I didn't want to interfere with those schedules, but to increase my sample size, I used some that had slightly shifted recording schedules. They were like 15 minutes on, 5 minutes off. After recording in the field, I would take all those recordings back to the lab, run them through a program called Raven, which visualizes them as spectrograms. And then I would look at our entire sampling effort for that song meter station, and I would choose a random calendar day, make sure that it didn't have excessive rain or wind, and then I would choose 3 to 6 consecutive tracks starting from sunrise, and those would be the tracks I would annotate. Initially, I chose 6 tracks because I thought that 6 was essential to capture the full biodiversity of the sites. Then about halfway through, I realized that 3 tracks was sufficient to capture the biodiversity, and I could actually cover more area and get more done by only doing 3 tracks. So that's the reason for the inconsistency. Then I would find all the vocalizations that were at least 5 decibels above background noise. So recording is never a clean and perfect ordeal. There's always some degree of background noise that you see as the gray fuzz there. And so to standardize things and to ensure that I could correctly identify the calls, I had to have that threshold above the background. Then there were some key parameters that I was interested in. In order to test the overlap, we have to know the start and end time of the songs. We also need to know pitches of songs. And then most importantly, like the peak frequency and the loudness of the songs. And I hope those definitions are helpful for folks who haven't done this kind of work before. Oh, the nice thing about Raven is that Raven will automatically calculate these parameters for us. So I did not have to do this by hand. It's a super useful program. However, what I did have to do by hand was add some important information. So we needed to know the species. I chose 4-letter codes because they are really quick and they're pretty easy to standardize. The call type, for this study, I kept it simple as just call or song. Whether there was overlap, 0 is no, 1 is yes. And then if there were details about that overlap, such as this is not a bird overlapping, this is an insect overlapping, or this is rain or something else. And let me define overlap real quick because this is a little bit nuanced. So the issue with Raven is that when you make a selection box, it doesn't fit the shape of the song perfectly. So sometimes you can get false positives. The boxes, so 222 and 225 will overlap, but the notes actually don't intersect. So I'm having a very strict definition of overlap as the notes truly intersecting with one another, such as 223 and 224. Okay. So I had nearly 24,000 annotations, and I did not do all of those by myself. So Saxony and Jen, if you're listening, thank you so much. I could not have done this master's in 2.5 years without your help. I'm really grateful to you both. Annotation queens. Okay, so you've done your 24,000 annotations. That's when the fun only begins. We're going to dive into some statistics. I'll try to keep it understandable for everybody. But the first thing is we want to look at the proportion of native versus alien species, because I believe that's what's driving the change in overlap. We also want to visualize frequency overlap and compare with the percentage of introduced species. And then we're going to run this null model, and this is the difficult one. So again, it's think of cutting up a track and reshuffling all the songs in a hat, and then playing them all out again, keeping their lengths and their frequency ranges the same. So do this 500 times, and then we're going to run a few different versions of this. So when we reshuffle the tracks, but we keep them within each 5-minute track itself for each site. Is overlap less or more than what we'd expect? We then repeat that process, but this time we're going to segregate those into native, alien, and alien vocalization pairs. Third, we repeat the above, but we only examine the songs because we believe that those are more important for signal partitioning or separation of songs. And then finally, we're going to do all the above steps, but this time we're going to look across the entire sampling period for a site. So that could be anywhere from 15 to 30 minutes. Okay, so first of all, the number of species or the species richness at a site seem to be related with the number of introduced species. And that's pretty simple to break down because there's a very limited number of native forest bird species left in Hawaii. And there's many more introduced species. So at that low elevation site, we're seeing a lot more species, but they're almost entirely non-native. Okay, so biodiversity is related to the proportion of introduced species. This one is a lot to unpack. Those different colors are different vegetation classes. I wouldn't get too lost in those. My song meter stations are represented by birds, and the larger sizes represent more overlap. The darker shade represents greater biodiversity, and then the warmer hue represents more introduced birds. So you'll see at Hakalau, so Hakalau's on the left and Pauka'a is on the right. And at Hakalau, generally there's more native species. There are some sections that have a significant amount of overlap, even though they are in native forest and it's mostly native species. And then at the lower elevation sites, they're largely introduced. There is some modest biodiversity. And then there's also less overlap. Looking at the frequency ranges across all species, so this is taking the lowest of the low and the highest of the high. Similar to what Pat and others found in 2021, there is a lot of overlap in frequency ranges. The darker shading on this plot shows like more frequently used frequency ranges. And I will say that species that have very small ranges on those, I think that's really reflective of sample size. We didn't get a lot of red jungle fowl and Java sparrows. That doesn't necessarily reflect the frequency range of those species. Okay, so the next thing that I did was I took this, so I actually averaged the minimum frequency of each species, the minimum frequency and the maximum frequency. I looked at which species actually coexisted with each other so that there was a meaningful comparison. And then I tested whether there was more or less or equivalent overlap in frequency between native-native pairings, native-non-native pairings, and non-native-non-native pairings. Okay, so, and I'm sorry, I used alien. So there's the most overlap between native-native pairs of songs in frequency, which is actually contrary to what I expected. These birds have been evolving together for millions of years. What's going on here? And then there's the least amount of overlap with alien pairs, even though these birds are coming from geographically very distant places. Let's see if the temporal partitioning helps to break that apart a little bit. So again, these are box plots, and just with what I showed in Pat's previous study, the box plots are showing the range of overlap according to those 500 randomizations. And then the interquartile range is the shaded region, the mean is the bar, and then our observations are the black dots. So what we wanted to do was see, we randomized the time again. So we wanted to see, is there overlap more or less or equal to expected? So any marked with an asterisk are significant. What do you notice? None have an asterisk. Oh no. Well, there is a pattern, right? They all are lower than what we'd expect. So they're trending lower, but this difference is not significant. And again, this is looking at each 5-minute track as its own individual unit. Okay, This next diagram is showing pairing by origin, so native, native, alien, alien, native, alien. And this is a standard effect size graph, which standard effect size represents the difference between means of observations and the null model. So in this situation, think of 0 as the null model. So, and then anything within negative 1.5 and positive 1.5 is not significant. So again, in this diagram, we're seeing that the origin of the bird, not only does it not play a difference in overlap being less than expected or more than expected, there's no difference from the mean of the random, but also there's no difference between pairing. So if a native bird is paired with a non-native bird, it's not any different than a non-native bird paired with a non-native bird. Okay, our third test. This is just looking at songs. This is a repeat of that first diagram. Again, do you see any asterisks? No, okay, but there is a pattern of them being consistently lower. And then finally, this is, again, looking at songs only, but this time we're looking across the whole sampling period. So that song had a chance to be randomized across 15 to 30 minutes instead of across just 5 minutes. And it didn't change our results at all. So contrary to what I predicted, the percentage of introduced species in the community doesn't appear to change acoustic overlap. But also contrary to what Pat and others found in 2021, there doesn't appear to be acoustic overlap happening. So let's unpack that a little bit. Why would I not see temporal partitioning, unlike in previous studies? Well, one reason why I might not see a difference from communities with more introduced birds and more native birds is that there's been a collapse in the acoustic community structure. So this is actually, there's evidence for this on Kauai. So Paxton et al. 2019 found that 3 bird species which had significantly declined in population size had actually started to have similar song structure relative to 50 years ago. And what that can be explained perhaps by is there's a loss of tutors. So birds need teachers to learn their songs. And if they don't have sufficient tutors, they're going to learn them from other species. There's also this idea of competitive release. So in Hawaii, there are very few avian predators. And I haven't studied this deeply myself, but that perhaps is one reason why we had such an impressive adaptive radiation of birds, is that there was a lot of competition for resources. When you remove competitors, though, suddenly there's an opening of resource space, in this case, sound space, that is available to that species. So it's possible that those extinctions and removing competitors, there's more bandwidth available for birds to use in their repertoires. Okay, then finally, this is why I think that my study had different results from Hart et al. 2021. There's seasonal variations in vocal activity. This is a acoustic complexity index diagram showing red-billed Leothrix in Italy across the course of the year. Main thing is that there are peaks and there are lows in activity. The peaks are the red, the lows are the blue. And I think that the fact that Hart et al. 2021 studied this in peak breeding season in March and April, and I used the summer months, could mean that this is a less important time for acoustic partitioning because there's less territoriality and less breeding of birds. Okay, the other thing is that we might be challenging the assumptions of the acoustic niche hypothesis here. So again, it assumes a pristine community. Hawaii is very disrupted. It has all these extinctions, it has all these additions, and Hart et al. Demonstrated that there was a lot less overlap in Costa Rica, which we would think of as a more intact biodiverse community than in Hawaii. So that could be another explanation. Other studies that found support for the acoustic niche hypothesis were working in very biodiverse environments. Then I wish that I had thought of this at the very beginning of my study, but almost no acoustic niche studies in birds, at least, account for differences in body size. So what this is showing on the x-axis, you have frequency, so a low frequency minimum, high frequency maximum, and then body size is shown by the size of those circles. So when you account for the constraints of a bird's mass, and generally birds that weigh more have lower frequency vocalizations, suddenly patterns that seem to be totally random kind of parse themselves out, and there's better evidence for acoustic separation within the constraints of birds' body sizes. So I didn't account for that. Someone really needs to. This has like really interesting applications. And then finally, what about other resource partitioning? So my study focused on acoustic niche space, but others previously looked at competition both between native and introduced species and then between just introduced species. And there seems to be like a carrying capacity for species. So as the number of introduced bird species in Hawaii increased, there was also an increase in extinctions. This is mostly occurring at low elevation places where there's not interaction with native birds. But the thought is, well, there's also these birds that have more similar beaks that only one of them survived and became established. There's a lot of biases and issues with studying these things because they were human facilitated introductions, but supporting island biogeography theory, we think that perhaps that there's some sort of resource competition between introduced species that's making there be like an upper limit to the number that can be here. We didn't find support for this with acoustic niche competition. I really think that future studies should incorporate playback more, and I wish I had considered this at the beginning. This takes a more experimental approach, and also previous playback experiments, mostly with frogs, have demonstrated that species do change their behavior in a very short time span to playback. Although I will caveat that with there was not only an effect from introduced species recordings, but often there was an effect from native species recordings, and there was an effect from white noise control. So there needs to be future studies to sort of separate those effects better. Okay, so finally, there was no effect of introduced bird species on native species partitioning of acoustic space in this study. There's no evidence of native species partitioning at all, though. And that's contrary to previous findings. So that could be seasonal variation. And then I think that future studies should look at the variation in acoustic niche use across seasons and see, is there better separation of vocalizations in peak breeding months than in outside of those? Okay, I really hope that if I've done my job and I deserve to pass, that you can answer all of these questions by the end of my presentation. So hopefully you know what passive acoustic monitoring is now. We've answered, hopefully you understand the answer to the question of whether introduced birds influence the amount of acoustic overlap. Now I'm going to focus on an application of passive acoustic monitoring. So can we estimate distance based on the maximum power level of recorded bird vocalizations on Hawaii Island? And don't worry, I'm going to define maximum power level. We survey wildlife populations, especially in Hawaii because it's mostly birds, using a distance sampling framework. And what that relies on is that an observer at point O detects an animal species at point A, and then using the distance between them, which is R, they get a probability detection function. What this allows us to do is, for the general public, when we do wildlife surveys, we don't get a head count of all the animals. Very rarely does that happen. Maybe if you're working in anchuline pools, but we have to account for all the animals that we don't detect. And in general, as the distance from the observer increases, your probability of detection gets lower. Okay, great, we've accounted for uncounted animals. However, there are some assumptions with that. And one of the big ones is that there's no error in your distance estimation. And we can calibrate each other all day long, but inherently there is some bias in how we estimate distances. And so there will be biases depending on the observer in the distance estimates for animals, and then that translates up to our estimates for density and abundance, which can have significantly different implications for conservation and management. Okay, fortunately, we can use the properties of sound to our advantage and maybe come up with better distance estimates that aren't biased. So this is using the relationship between sound pressure, which is simply the pressure of a sound wave relative to the air pressure around it. You may also hear me refer to this as power level, and then the distance between that bird and the recording device. This is an inverse relationship, and we usually measure sound pressure level or power in decibels. So previous work done in our lab, Sebastian Gonzalez et al. 2018, tried to get unbiased distance estimates by going out in the field, recording birds, and detecting their exact distances through rangefinders, and then using a generalized linear model to fit those distances, and then the loudness or the power level of those vocalizations, which was on the recording device, and see, can you predict distance from power level? And actually, there was a significant relationship between the two for Amakihi calls. And this was based on only 62 vocalizations, so you don't need an insane sample size to do this. Okay, great. Also, Sebastian Gonzalez et al. 2018 had the foresight to account for weather, and we decided to incorporate this in our study. So wind can distort sound waves, and by distort, I mean change the shape of them. And also rain can increase attenuation or the loss of energy of sound waves. So something can sound like it's further away if it's rainy, if it's wind, depending on if the wind is at your back or in front of you, the sound can sound closer or further away. And so they used a 3-point scale. We used a modified version of that and adjusted, and I'll talk more about that later. Another study, Yip et al. 2019, looked at 2 bird species, and they actually compared different ways of estimating distance. One was using an acoustic grid, which is a bunch of different song meters, evenly spaced, synchronized in time, and then timing the arrival of the bird vocalization to the song meter. And then the second one was using an observer with a playback speaker who would attract common nighthawks, and then use a recording device to record the common nighthawk's responses, and then also measure exact distances to the common nighthawk. So those exact distances were modeled and density was estimated from those, and those were compared with the estimated distances based on the relative power level of those recorded calls. Okay, so in both cases, this is an ovenbird, by the way. So in both the time of arrival method and in the common nighthawk method, the distance using power level, it significantly reduced the error bias and distance estimation from human estimated distances. That was a third comparison. Actually, in the case of the power level, it completely removed the error bias, even better than the time of arrival. And then density calculated from distance estimates from the sound level were equivalent to the density calculated from the known distances. So remember, that observer was also measuring exact distances to the bird as it flew in and vocalized. And they found that 300 vocalizations was necessary to calibrate the model. So this is a more sample size than what Sebastian Gonzalez et al. Found. Okay, what neither study accounted for was directionality. And I think this is important, honestly. Orientation of a bird to the observer changes how that sound propagates. So if a chicken's facing you and it's cock-a-doodle-doodling, it's going to sound a lot louder than if it's facing away from you. And I hate talking to an audience like this. Okay. My question was, can we use distance to be an accurate estimate of power, from power level for multiple Hawaiian bird species using our acoustic recording devices? I thought that there would be an inverse relationship between the two, just understanding the relationship of sound to distance and previous studies. I thought that bird orientation that was closer to the observer, so closer to 0 degrees, would increase the slope of that relationship between distance and power level. I thought that relationships would be different based on call types because, remember, species have different body sizes and different constraints. Also, call types have different functions, and I'm going to dive into that more later, so stay tuned. Finally, higher levels of wind and rain would drive those slopes down because it would make attenuation and the changing of the shape of the sound waves greater. So back to Hakalau. What we would do is, in pairs of observers, we would start the recording device. We would identify a vocalizing bird, measure the distance to that bird while it's in sight and vocalizing. Also record the orientation of the bird to the observer, estimating to the nearest 10 degrees. And then we would move on and repeat. And sometimes to increase our sample size for distances, we would repeat observations from the same individual. But we try to cover a large amount of ground and get a variety of species. Then back in the lab, fortunately, we had written down the time that that vocalization occurred, so it was really easy to just scan to that selection or that vocalization and select it. Raven would measure the same parameters that I've already mentioned. We would add in our own parameters, remembering that we recorded the orientation in the field, we recorded the exact distance from the rangefinder, and then we also accounted for wind and rain. We estimated this on a Beaufort scale, which is a bit of a more subjective scale than what Sebastian Gonzalez et al. Used, but then we converted it to their scale because we didn't have a weather station. Okay, then there were two ways that I wanted to examine this. One was looking at the overall pattern. So across species, we have a pretty large sample size. Is there a general pattern between distance and power level? And then finally, I wanted to fit generalized linear models for individual species because I figured for the purposes of wildlife monitoring, it would increase our precision because there's likely species-specific relationships between distance and power level. Okay, so 15 species later, 23 vocalization types later, and 731 vocalizations. Keely knows all about how painful this was. We have our global model, and there are significant relationships from power level, from wind, and from rain. Also, only four of our generalized linear models had significant relationships. Most of them were not predictive. So I'm going to unpack these a little bit. The general model, I used model selection with Akaike's information criterion. Basically what that means is I chose the model that had the best fit and also paying attention to the middle value, which is the conditional R squared. So what you're going to see is this R squared value is much higher for the individual species specific models. Again, when the purpose of the model is just to achieve the best fit, I think that separating that by species and call type is really important. Okay, so our first one, I'm going to play an Apapane song for you. Okay, there is relationship with Apapane song and distance. There is also, unlike the global model, there was an effect of orientation. So I was right about that. Next was EV call type 2. And again, there's also an effect of orientation. Some of these variables had to be logged because there was a strong right skew. In other words, it was really hard to get birds to perch on top of our heads. So we had a lot of observations of birds that were further away from us. Warbling wide-eye Twitter call. And yellow-fronted canary song. Okay. So in the larger model, which is fitting the overall data set, we didn't have an effect of orientation. Why is that? Well, the directionality of signal often relates to the function. And I should mention that while my song meters were off recording in the summer months, observers like Keely and I were going out and collecting these observations. So these were, again, not collected during peak breeding season. And Patricelli et al. 2007 found that generally signals such as mating calls or mate solicitation calls were directional because the cost of eavesdropping is greater. So you don't want others of your own species, or even worse, predators, to overhear you. But other signals such as alarm calls, like, oh, there's a mink hiding back there, were more omnidirectional. So it's possible that the overall fit of the data, we had very few relationships because so many of those vocalizations were of the more omnidirectional kind. And on the farthest right, this is just this is a really cool study. They had perches and they had as equally as possible spaced microphones around those perches to see if the direction of the song was equal to all of those spots around the perch, or whether it was higher or lower between the different spots. Okay. Lack of relationships also could be explained by just the fact that sound almost never propagates in its ideal environment. Constructive and destructive interference occurs from just other noises in the environment, whether it be birds or cows or whatever. Also, attenuation, we didn't think about this at the beginning, but attenuation can also change with temperature and humidity, and we should have accounted for those factors, but we didn't. Attenuation also isn't uniform across frequencies. So remember, that's the loss of energy of sound waves. Higher frequency sounds tend to travel better in open environments, and lower frequency sounds travel much better in dense forested environments, similar to what we were surveying in. Interestingly, our results are perfectly consistent with that because most of those species models are in the higher frequency range. So I'm not sure what's happening there. Birds can also, just like us, change the loudness of their vocalizations depending on the context, such as the presence of other environmental noise. So I think that individual variation is a difficult one to account for, but it's probably playing a significant role with our distance estimation abilities. I think that in the future, you could compare SPL distance estimation or power level distance estimation against time of arrival, similar to what Yip et al. Did in 2019, but they only did, they did different species for each method, so that's one confounding factor, and they only had 2 species. I think this should be done for a variety of species. Also, what if you experimented with an acoustic array, not just for time of arrival, and I mean multiple recorders, but what if an acoustic array could also help you improve your distance estimation from power level? Third, you could incorporate distance estimation for power levels with Q rates, and that's actually what Sebastian Gonzalez et al. Did in 2018, but again, she only used 1 focal species. And then fourth, try experimenting in different habitat types. Likely those models need to be fitted differently depending on if you're in dense forest or in an open field. Okay, so consistently, the maximum power level, so the greatest loudness of the bird vocalizations was the strongest predictor of distance. There were some effects from wind and rain. Orientation didn't have an effect for the larger fit of the overall data, but it did have an effect for individual species-specific models. And then those 4 call types showing a relationship gives some evidence that there is potential for species-specific distance estimation. Although it may not be effective for endangered species where you have a limited sample size, or for species like oma'o that modulate their songs a lot. So personally, I think distance estimation could improve with refinement of these methods, although there may be better alternatives, such as time of arrival, that should be investigated. So thank you so much for listening. Thank you for all the people who have made this possible. I wouldn't be here without you. And yeah, let's go get drinks afterwards. Okay, I'll take any questions. I'll check the Zoom folks. Oh, I do have Paul Banco. I'm gonna unmute you, Paul. If you prefer to ask over chat, that's also okay. Let's see.
So are you able to hear me, Noah?
Yeah, I hear you, Paul.
Oh, okay. Yeah, that was fantastic. I really appreciate your work. It's just outstanding. I did have a question, and you sort of alluded to the question earlier about is there an effect of vegetation density on the power level? And so, I mean, most of the calibrations that you performed were done where you could see the bird. There was nothing between you and the bird, or very little.
Mhm.
And I'm just wondering if a bird is singing in the in the dense uh, growth of trees, is that going to affect the power level? And if so,
Okay. Paul is out doing Galila surveys, so we may have lost him. Oh, wait, you're still here, Paul. Hey, Paul, do you think you can type that one in the chat? And I'm gonna circle back to you. I think you were getting at, the differences in sound traveling between different, habitat structure or vegetation type structure. Okay, let's see. One thing that he brought up was that it's much easier to observe birds out in the open, and that is an inherent bias of this study. So it was really difficult to get observations in the dense, continuous primary forest. And also there were human safety concerns of following birds on that transect. So you'll notice that, we were primarily targeting forest edge or open areas. And I tried to keep this fairly consistent across our sampling locations within Hakala. We were in the Puakala and Pedro units. And I did not actually compare between sites because my assumption was that they would be comparable, although maybe I should go back and actually run that comparison just to make sure that they are standardized. But yes, that is an issue with this method. And that's one thing why I think it's limiting, is that if you want to calibrate your distance estimation framework, first you have to get the exact distances of the birds, and that's going to be very challenging to do in primary forest, and especially in really remote areas where there are no trails. So for sure, that's a limitation of this study. Let's see if Paul got back. All right. Yeah, I think he went back to Chase Blue. So anybody else? Oh, okay, great. Okay, I think I got that one. Okay, Rick had a question between signal strength and distance estimation. I think you should be able to unmute yourself, Rick, but if not, I'll unmute you. There we go.
Awesome presentation, Noah. Thank you. So with the work that Esther did, looking at the relationship between signal strength and distance, one of the things that we found with Oma'o was a strong bias because of the orientation of the birds. Is there a way, using your data, without being able to collect orientation on individuals, to then put it in the same framework of Esther's distance estimation? Or do you think that that won't work because orientation has to be accounted for?
Yeah, that's a good question, Rick. So that was one thing that I didn't unpack in this, is that it's not, if the effect of orientation is significant, like in those species specific models, does that limit its functionality if you're trying to just use acoustic recordings to be able to predict distances? And the whole point is that you don't have that visual component. So you can't see you can't see from a recording device whether the bird is facing you or away from you or somewhere in between. So the best answer that I can come up with is using multiple recorders. I think that using multiple recorders, similar to what Patricelli et al. Did, I can go back to that slide real quick. Those, testing for directionality. Let's see. Here we go. Yep. This one. Okay, so if you were to kind of morph this framework with the acoustic array framework where you had multiple microphones, I think that you could help to estimate orientation. Although I will say at that point, then depending on how many recorders you can afford, you might as well be using time of arrival. But I think that there's value in looking across those two different methods. But yeah, I will say that I didn't put up the estimates and p-values for the slopes of orientation. I will say that the effect of orientation was pretty small. It wasn't explaining a significant amount of the variation in the data set. Was much more important. And usually, not always, but usually weather was more important. So yeah. Orientation might need to be like a parameter that is dropped if once you've calibrated your data set, you have good data, you have field observations, you've controlled for vegetation types. Once you have that calibrated data set and you're ready to just take it and go with it on purely recorded audio, you can probably either drop orientation or find a different way to account for it.
Can I ask a follow-up question?
Yes, please.
If you're putting an array of recorders out, instead of recording time of arrival, could you instead use the array to triangulate to the bird and thus get an exact distance?
Yes, so some triangulation methods are actually using time of arrival. Other ones don't need that. But yeah, so a lot of triangulation, so similar to telemetry, it's using the time that sound was received to estimate, and then comparing that with another receiving unit that's synchronized in time to figure out where that sound was localized. I think a lot of those other triangulation studies are actually using time of arrival in some way. I'm not as familiar with the ones that don't, but yeah, I mean, I think the more methods that you can try and compare and then use the best one that you can reliably get estimates for, I think that's a good approach.
Awesome. Thank you, Noah. Congratulations.
Thank you, Ray. Yeah, Zach.
First off, awesome presentation. So you mentioned that like seasonality, they're more vocal, right, than others, and potentially being in the summer there is less vocalization. I think you referred to the birds in Italy for that, right? Has someone done that study in Hawaii, like showing that it is definitely different in those seasons? Like, do you think you would have gotten different results if you would have done it during a different time of year?
Yes, and I regret that. I think it would be also really simple it wouldn't be simple from an annotation perspective. So the limiting factor here is that the rate limiting step is we can't use artificial intelligence to automatically select songs and know that there's two songs overlapping. So we have to do that all by hand. But if we could hire more annotators, or God forbid, extend my thesis another year, I just got death glares from Lauren and Rick there. I didn't even have to look at Rick. So I would compare to see is there a significant difference in overlap between March and April, and then like June through August. And maybe there is no significant difference in overlap. That would be a really easy way. That would be like a very low grade way of doing that. But to answer your original question, on the level that, Farina et al. 2014 did, with the Leothrix in Italy, looking at, acoustic complexity index across the year, or acoustic activity levels, nobody has done this kind of stuff in Hawaii, and this is probably no better place to do it because so much of our understanding of endangered bird populations, when we're not going out and doing the forest bird surveys every so often, is going to be tied to this. You know, are we getting reliable estimates because we're estimating, you know, Maui parrotbill or kiwikiu populations at this time of year? If you could see my cursor, oh, you can't. What if we're estimating an endangered bird population in the blue time of year as opposed to the red time of year? That has significant difference in our estimates of population density and abundance. So, and I think that that's already built into the forest bird survey framework. They survey during the peak breeding season, but it's good to see if there's other effects too throughout the course of the year.
Yeah, I think it's really interesting, and it's always, you know, when we have different results in our digest, it's like, ooh. How can we compare this?
Yeah, sometimes we can step on their toes that way.
Intimidating results are read over. But yeah, thank you, that was awesome.
Yeah, exactly. Yeah, Dr. Freud.
Well, again, thank you very much for the presentation, all the work. I had a question about some of the plot figures, and in particular, the one which was sort of a summary figure with all the dots from one side of the line. Could you pull it up?
Let's see. Oh, the standard effect size. This one.
Yeah, so it's just very interesting to me that they are all on the negative side. And I'm just curious if you could maybe talk about that a little bit more. And are there any situations where you might expect it to be on the other side of the line?
Yeah. So I talk about this in my manuscript, and for the sake of just, you know, being more concise, I didn't talk about the acoustic clustering hypothesis, which may not be mutually exclusive to the acoustic niche hypothesis, by the way, but it's contentious. There's an idea that rather than avoiding shared signal space with other species, birds might be actually like jumping on the same bandwidth as other species, and that somehow that could actually amplify their communication or have other sort of benefits. So according to that hypothesis, Tobias et al. 2014, you would see things on the other side of the diagram. So you would see convergence of song and more overlap than just randomly expected. So yeah, it is interesting, like both with the standard effect size and with the box plots, that it's consistently lower. I have some homework. I didn't make it into this presentation, but I need to do a sign rank test and see, like, okay, if there's no effect and if it was perfectly random, you would expect there to be dots on both sides of the null mean, right? So is it coincidence that it's significantly lower? Maybe not. So the sign rank test could help me determine that, and at least say, it's not going to tell me that there's a significant effect, but it will at least say, like, there could be a hidden effect, you know, there could be something else going on that is quieting that effect. Did that answer your question?
That's still a very interesting pattern that I don't understand.
This one?
Yeah.
Okay, so basically it's not departing significantly, you know, it has to be greater than 1.5 or less than negative 1.5 to be different from the null mean.
Sure, but there is some directionality, right?
But there is directionality, so yeah, I was surprised that it wasn't significant, honestly. And that's why I want to do the sign rank test. Yeah.
Yeah, I think you're onto something there, Brian, for sure. Especially also with those box plots too. I mean, if there was no effect, it wouldn't be under every single time. And so it's almost like there's additional stats you could do. Because that's kind of summarizing the data in that, then you can do an additional test to see if there's an overall effect. Because with the null being that you'd expect similar amounts above and below if it was random.
So with the Hardball study, can you go back to that?
Yeah.
The majority of those below, I mean, regardless of the fact that they were significant or not,
Yeah, they were
Yeah.
significant.
but were the majority of them below too?
Yeah.
Yes.
Right, so there's
Yeah,
consistency.
it's below, but just a little bit further below the.
Right.
is-
Yeah.
Right,
Just
but that may
further
be
below
a
that.
seasonal
Could be,
effect, and so the effect's there, but it's just not strong enough.
yeah. You actually don't see the effect until you do it multiple times at different locations like you did.
Right.
Yeah. Also,
Yeah.
not all of Pat's song meters had a significant effect. So the second
Yeah.
one, so HI2, and then the fifth one, HI5, it was similarly below the mean null, but it wasn't significantly below. So,
But they're all below,
but they're all below.
and yours are pretty much all, for that one model, are all below.
Yeah,
Yeah, there's definitely something there.
yeah.
Statistics. Wouldn't you expect clustering to occur, almost like in a LEC system, during the breeding season, however? You mentioned that as an alternative. So
So-
that idea is like larger LECs bring in
Yeah.
attract greater numbers of females.
So
Wouldn't you
what I
expect
thought,
clustering then?
yeah, good question, Adam. So, and just for those who aren't familiar, a LEC system is where there's kind of, there's a stage and all the males come and perform on this stage for females because the females know to find that stage. And then the fact that at least one male is performing, everybody kind of cashes in on that. Like, oh, if he's attracting a female, I have a chance to attract a female. So what you get is you get synchronous courtship displays or oftentimes songs. And so Adam's asking like, would you see more overlap? So this is another nuance. There's heterospecific overlap, and these overlap pairings that were both looked at in Pat's study and in mine, these are between only different species. That's because a lot of signal overlap within a species is sometimes intentional. Males want to like out-sing the other male. There's counter singing. Some species, the males and females duet, and that's part of their territorial defense, like in redback fairy wrens. So, yeah, so that's something like, there are studies examining acoustic niche partitioning within species, but there's so many caveats to that because of a competition between males and things like that. Yeah, but following that observation, I would think during the breeding season, there would be a lot of intraspecific or within a species overlap. And then I would think there would be more interspecific separation of vocalizations because it's more important that you're not interfering with another of a different species. It's one thing if a bunch of Apane are going for the same female. It's another thing if you're just trying to like not be crowded out by the EEV and get your signal across to the right species. Okay, Lauren.
Going back to the birds that did have a significant effect for distance and radiation.
Yeah.
So have there been any studies that are looking at the reason or the meaning behind those calls? So you mentioned that the meaning behind the calls has a difference on the like directionality of it. So whether it's omnidirectional or going specifically to one bird. Has there been any studies looking at what like that song might mean, or do you have any hypotheses of maybe what that means since there was significance to it?
Yeah, good point. I honestly, I didn't go into the weeds with the functionality of call types. And also our call types are perhaps like subjective. Yeah, we tried to keep things consistent between observers, and we thought that there would be different properties of sound according to the call type. But I will say songs, those are one of those that, according to Patricelli, would be directional. And we had an effect of orientation. So that's consistent with that. You know, EV call type 2 may actually be more of a mean, incorporating some song elements in there. I don't know the function of that song. Twitter calls are essentially like an alarm call. They're the bird alerting others of danger or disturbance. And I was surprised to see an effective orientation in that one. That's one where we would predict that that would be a more omnidirectional signal. And then finally, the yellow-fronted canary song, it's a song. Again, I would predict that to be directional, which is consistent with orientation having an effect. So I think that it's interesting, 2 out of the 4 vocalization types that did have significant relationships were songs. I would think we have a small sample size, but I would think that a higher proportion of those would be purely songs, although this was in the non-breeding season. Okay.
Well, Management committee has a lot more questions, I know. It is 9:46 right now. So if there's no more questions, we could probably just ask more in our committee meeting following up. Yeah, great job, Noah.
Thanks, everyone. Means a lot to have you all here. And if you do have questions, my whoops. Oh, I guess my email is at the very first slide. Let's see how fast I can click. For those on Zoom, for especially. Yeah. Further questions, shoot me an email. You can hunt me down in Wentworth 19 or find somebody who knows me. Thank you so much.